topological problem. Seems to be getting worse. Topological problem. Okay, so let me recall. Let's see. Are we going to collect the assignments at the break? Yeah. Okay. So let me recall that if you have a Lipschitz map from X to Y, these are metric spaces. Lipschitz. And if you take an, this is just A contained in X. Where X and Y are metric spaces. And you remember we proved that the Hausdorff measure of the image under that map is less than or equal to the nth power of the Lipschitz constant times the Hausdorff measure of A. So A does not have to be measurable there. That's for any set A contained in the metric space X. Now we want to give a slight a refinement of this. Before I state that refinement, let me just make one point that we haven't talked about before. That is that if you look at a zero-dimensional Hausdorff measure, what is that? According to our definition, it's the sum omega m diameter of Cj, it's the infimum. So this would be omega 0 in this case, and diameter Cj over 2 to the 0th power, right? That would be that. Now this, and we want the inf of that. Well, this is always 1, right? There's, even 0 to the 0 is defined to be 1. So this is counting measure. This is the inf taken over all countable collections with A contained in the union of Cj. Well, you see, that's just counting measure, right? It's that's H0 is just the number of points. In A. Of course, that might be plus infinity if it's an infinite set, but if it's a finite set, it's the number of points, possibly. So so zero-dimensional Hausdorff measure is just counting measure. It just simply counts the number of points in a set, and that gives you, and it's plus infinity if the set is an infinite set. Okay, so we want to give a refinement of this result here, and that goes as follows. So again, X and Y are metric spaces. Got a Lipschitz map, A contained in X, so X and Y metric. A is a subset, and now we do want it to be measurable. So A contained in X is required to be Hn measurable. Then you get a slightly better result. Well, first of all, Oh yeah, I forgot one hypothesis here. X and Y are metric spaces, and we also assume that X is sigma compact. Sigma compact. That just means that X can be written as the countable union of compact sets Kj. So Hn measurable and Hna finite. So they're the hypotheses. In particular, don't forget this hypothesis. What I'm about to say is not true without that hypothesis. And so you take a Lipschitz map, and the first conclusion is that the image, that's this thing that we were talking about here, that is indeed measurable. You should be a bit careful about this. Remember, if f is merely continuous, it's false in general that fa is measurable. But if f is Lipschitz, I claim if f is Lipschitz, this is a true fact. So we need to check that. And the second thing is that the measure of that in fact, you can improve this inequality. Of course, this is still true because we've got the same hypotheses as we had before. So this is still true, but I claim a slightly better inequality is true. Namely, this time the integral of the counting measure of the pre-image of any point y integrated with respect to hny. Y is the variable here. So f to the minus 1y, as usual, means the pre-image. It's the set of x back in A such that fx equals y. It could be a big set, or it could even be empty if there's no x such that fx equals y. So this is the integral over the space y, the hny. That is less than or equal to just lip f to the nth power times hn of A. Now notice this is the so-called multiplicity function. In fact, that's what it's called. It's the multiplicity function of f. Multiplicity function. It counts the number of points in the pre-image. It's plus infinity if there's infinitely many points in the pre-image. And otherwise, it's the finite number of points in the pre-image. It's a multiplicity function. It's just this counting measure. Just count the number of points. Now notice that, of course, duplicates this result because this is always bigger than or equal to 1 when you've got a point in the image. So this is certainly bigger than or equal to hn of fa. So it's consistent with what we proved earlier. In fact, it's an extension of that. Okay, so let's so that's what we want to prove first today. So let's check this. Well, let's see. A proof of 1. HNA is finite. So we can use the regularity theory that we developed before, and so A is contained in also the sigma compactness, you see, guarantees that A is contained in a countable union of compact sets. So A is contained in a countable union of compacts. So in fact, we can rewrite A equals the union, a disjoint union, J equals 1 to infinity, AJ, where each AJ is contained in a compact set. so, and each AJ is measurable. And we can make this a disjoint union. So that's the first step. Let's do that. And then we can decompose this, take any integer, any positive integer. Then we can decompose this further into sets of diameter less than, say, 1 over I. Right? So we can write AJ equals the union I equals 1 to infinity AIJ. And not only that, we can do this in, so with diameter Aij less than 1 over I. Okay, we can certainly do that. Notice that follows from the fact that this is contained in a compact set, right? As soon as it's contained in a compact set, you can cover that compact set by finitely many balls of diameter less than 1 over I, right? And that's what gives you these sets Aij. So we can certainly do that. So we decompose, and then, yes, okay. And then, I think I'm proving this one right, aren't I? Yeah, I'm supposed to be just proving one. Okay, we're going to use this in part 2, but I'm supposed to be concentrating on part 1 at the moment. So let's just finish part 1. That's the easy part here. So let me finish part 1 here. So this proof of 2. Okay, so let's see, what's the conclusion of, what's the end of the proof of part 1? Well, each of these AJs, by the regularity theory, remember we proved that you can always approximate a measurable set for a Borel regular measure, which, remember, Hausdorff measure is Borel regular. You can always approximate the measure of a set, a finite measure, by taking closed sets inside the given set. So by regularity, there exists compact sets C1, C2, etc., with Hn Aj minus the union of Ci. So I guess these, I suppose if you want to be picky, these depend on which J we're talking about. So I suppose I really ought to label them with 2 indices. So let's call them Cj1, Cj2, etc., compact sets. And Aj minus the union I equals 1 to infinity Cji equals 0. So let me do that. So that's just the regularity property of Borel regular measure. You can always approximate a Borel, a subset. With respect to a Borel regular measure, you can always approximate a subset from inside by closed sets. One slight subtlety here is to remember that normally you have to use closed sets rather than compact sets, but remember the Aj is already contained in a compact set, so these sets can be taken to be closed, taken to be compact, no problem. So we do that, and notice that implies that Faj, the image, can be written as F of Aj minus the union of Cji, I 1 to infinity, union with union I equals 1 up to infinity F Cij. So Cji rather, like that. So we can do that. Now notice that each of these guys is compact because the image of a compact set under a continuous function is still compact. So that's a compact set. So this is a countable union of compacts. So this is a Borel set. Countable union of compact sets. Certainly a Borel set. Whereas this one is a set of measure 0, as we just said here. Now, that's got measure 0. But what about the image? Well, we can use this inequality, which we've already proved last time. That if A has got measure 0, then so does the image of A by this inequality. So that means that this image has also measure 0, Hn measure 0. So that's great. We've written Faj as the union of a set of measure 0 and a Borel set, so it's Hn measurable. So that takes care of part 1. Notice we only had to worry about Aj because now, of course, the f of A is the union of these, so that's still measurable, countable union of measurable sets. So that takes care of part 1. Got that. Now let's go back to part 2. We were doing this using the same Aj's, and we decompose with diameter Aj less than 1 over I. And now let's look at the image. So yes, so right. We're interested in the Hausdorff measure of these Aij. So this is a disjoint union. Disjoint union. And so Faj, yeah, so Faj, so let's look at this, let's look at the sum of these measures. Hn Aij. So we're taking the sum of all these pairwise disjoint sets. That's, oh, sorry, I'm supposed to be looking at the image, aren't I? Supposed to be looking at the image. So let's look at the image sets. Now notice the image sets are not necessarily pairwise disjoint. So let's mull this over a bit. This is a slightly subtle point. So I'm taking the sum of all the images of these pairwise disjoint sets. Now, of course, these sets are not necessarily pairwise disjoint. F is not necessarily a one-to-one function, so these can be overlapping. And notice that this can be written as the integral. This is a nice trick, actually, that you should remember. This can be written as the integral over y of the indicator function of F(Aij) at a point y with respect to Hausdorff measure, where y is the variable of integration with respect to the Hausdorff measure. Now let's check that that's correct. Notice that chi a, as usual, is the indicator function. That is, if you take a set C, then chi cy is equal to 1 if y is in C, and it's equal to 0 if y is not in C. So let's think about this. This is a sum still, so that's a sum I equals 1 to infinity, like so. And you can take the sum outside. Remember, these are all non-negative terms, so you can simply take sum outside the integral. And then this integral, of course, gives you back this. The integral of the indicator function is, so this is certainly a correct identity. But the nice thing about indicator function is that if you stare at this, you'll see that, in fact, this measures as j tends to infinity. Let's see, have I done the wrong thing here? I should have union I equals 1 to infinity. Yeah, this is wrong. I'm supposed to be taking union of j, Aij. No, that's correct. Diameter I less than 1 over I. Seem to have something messed up there. Hold on one sec. Right. Okay. Yes. Yeah, this is supposed to be the sum over j. Sorry. We're supposed to be taking sum over j here for fixed I. diameter is less than 1 over I. Sorry, so I've messed this up. This is union J equals, so A, right, so let's just say it this way. All of A can be written as a union, can be broken up as a union J equals 1 to infinity. You can do that for each I. Just think about that. In order to achieve that, you can use these sets A, J from the first part, for example. But it's clear that you can do that. So I can rewrite all of A as the union from J equals 1 to infinity, Aij, where these are disjoint, and diameter of Aij is less than 1 over I for each I. So then this is supposed to be a sum over J. That looks better. And this is J equals 1 to infinity. That's better. Now, as I said, there's a nice point here. Each of these has diameter less than 1 over I times the, notice this set here, has diameter less than Lipschitz constant times 1 over I. Because each of these originally had diameter 1 over I at most, less than 1 over I. So that's less than, the diameter is less than lip F times 1 over I. Now think about the possibilities. Suppose the pre-image, f to the minus 1y, just think for a minute, imagine for a minute that that's just got finitely many points. Like so. So the picture would be something like that. This is this is the set A. This is the space X, and Y is here, and F is going here. And we're taking a point Y here and looking at the pre-image. So we're looking, and just imagine for a minute there are just finitely many points in the pre-image, x1 up to xn, say, for example, mapping to this point Y. Well, as soon as lip F times 1 over I is less than the minimum distance between these, less than the minimum over j not equal to k of xj minus xk, then these points are in different sets, aij. X1 up to xn are in distinct sets. aij1 up to aijn. The aij's are sets back here, sets of small diameter, less than 1 over j. In fact, that's true as soon as 1 over I is less than that, actually, because these sets have diameter less than 1 over I. So as soon as 1 over I, as soon as I is large enough to get you here, then these are in distinct sets. So that means that we have then n terms, not n terms here. So this will be n in that case. So you see the point is that this is one of the nice things about indicator functions, that the sum j equals 1 to infinity of chi f aij, the image, the indicator function of the image set, that is eventually increases to the multiplicity function. Eventually there'll be n distinct sets. In fact, as soon as 1 over I is less than the minimum, h0, f to the minus 1y. So that's very nice. It's except that I cheated you again a little bit here, sorry. I forgot to say that I want this to be actually increasing to this. And in order to do that, I've got to make sure I select these sets inductively. Select the aij inductively. That just means that when I'm selecting the ai plus 1 j's, I make sure that each ai plus 1j is contained in one of the previous selected sets, aiq, right? So we want to make sure that we we get an increasing sequence here. So let's agree on that. We do this inductively so that we have this inclusion. And that does mean this is increasing then, right? So we get an increasing sequence converging to the multiplicity of the preimage. That's one of the really nice ideas, one of the nice elementary ideas of using indicator functions. So this, by the monotone convergence theorem, tends to the integral h0 of f to the minus 1 y, integrated with respect to hn. With respect to the variable y, and this is over all the space y. That looks like a big integral, but remember this is only non-zero when y is in the image of the set A. Otherwise it's 0. So this is really only, notice this is the same as integrating over the image. It's exactly the same thing because this is 0 when you're not in the image anyway. Okay, so that's the proof of that result. So indeed, this is this converges to that, and of course this is less than or equal to lip f to the n by the previous result, this one. This is certainly lip f less than or equal to lip f to the n times the sum hn aij. J equals 1 to infinity, but that's the same as, of course, these are pairwise disjoint, so this is exactly the same as the measure of A. So lip f to the n times hn of A. So that's the theorem. So we have this. Okay, so that's nice. Now one very nice extension of this is thinking about whether you could extend this to when, instead of using counting measure here, you use the k-dimensional Hausdorff measure. And that's what the next theorem is about, a really nice theorem that's very useful because it gets you bounds on these preimages. See, I should mention this, that here's the sort of picture that we should keep in mind, that you've got this function, this is in the metric space f, x, and then you've got a function mapping into the metric space y, and you consider the preimage of various points y. Well, typically that will give you, that sort of divides A up into disjoint slices. Preimage is by definition a disjoint, of course. So it divides A up into what you would call slices. Whose union gives you all of A. So you would like to understand various things about those slices. And the next theorem that I'm about to tell you about is, talks about the k-dimensional Hausdorff measure of these slices. That can be extremely valuable in analysis, to get bounds on the various Hausdorff measures of the slices of a function. You often want to cut sets up into slices using a function f in this way. So rather important theorem. So here's the theorem. Here k is just bigger than 0. It needn't be an integer in this theorem. Maybe a fraction. Maybe fractional. And you've got the same setup as before. X is a sigma compact metric space. Sigma compact metric space. And this time we're going to be, it's not quite as general as this first theorem, because this time we're going to be mapping into Rm rather than into a general metric space. So A contained in X is, and suppose that this is Hm plus K measurable. this time we're going to be talking about k-dimensional slices. So the relevant thing to talk about with respect to A is the m plus k Hausdorff measure. So hm plus k measurable and hm plus k A finite. And sigma compact, and F is a map A into Rm, where m is in 1, 2, etc. Like so. Then the integral of the k-dimensional Hausdorff measure of the slice that you get from F. That's the pre-image of y, taken over the space y, integrated with respect to m-dimensional Hausdorff measure, is equal to, or rather is less than or equal to, it's going to be an inequality like this one was, less than or equal to lip f to the mth power times hm plus k A. Except that there's a slight complication. You get a slightly different constant here. You get the constants omega k times omega m over omega m plus k, which looks a little bit mysterious at first sight, like so. And the claim is that that's the inequality. Now, once again, remember, this looks like you're integrating over all of y, but you're not really. You're really only integrating over the image of A, because this, in any case, is 0 if f to the minus 1y is empty. So it's really the integral over FA. Okay, so let's see if we can prove this one. So first step, you should divide A up, we should approximate the measure of this. That's the first step, to take an approximation of that Hausdorff measure. So let I be any integer, and pick a covering CI1, CI2, etc., with diameter Cij less than 1 over I, and let's pick them so that we get reasonably close to the 1 over I size approximation of this measure. So hm plus k 1 over I of A, sum j equals 1 to infinity, omega m plus k, diameter Cij over 2 to the m plus k power is less than or equal to hm 1 over I, A plus 1 over I, for example. Now that's clear you can do that because remember, this size, m plus k, we're talking about the m plus k Hausdorff measure. So we want to take the m plus k size 1 over I approximation to that. And remember, we can do that because you get, this is the inf. This guy is exactly equal to the inf of all such coverings. I forgot to say A contained in the union j equals 1 to infinity Cij. So this is exactly the inf over all such coverings. So we can get as close as we like to the inf by picking a particular collection. And for instance, I'm saying you can get within 1 over I of that. That's no problem. So we can certainly do that. And now let's think about this. Think about these sets. Now, notice that F Cij intersect A. What about that? Let's look at F there. Now, F is a Lipschitz function on A, and A is not necessarily closed, of course. It's just a measurable set. So I'd like to make an extension of F so that we can work in the closure of these for a reason that will become clear in just a minute. So I'm going to make an observation here that if you take F, it's Lipschitz. This is what we're given, mapping into Rm. That's Lipschitz. And think about a point, say a sequence, rather, of points, say xk in A, converging to a point x in the closure of A. Think about that situation. Well, F is Lipschitz, so that means that then F, this is a Cauchy sequence then, so xk is Cauchy. A sequence where k equals 1 to, oh, I guess k is a bad choice for notation here because I'm already using k as the variable, so let's use something else. Let's call that xl. Okay, so L equals 1 to, etc. So that is Cauchy, of course, because it's convergent. And oh yeah, sorry, x is converging to x. So that may or may not be true because I don't think I'm assuming that the space x is complete. So that may not be true. But what is true is that the image points form a Cauchy sequence. Because notice that f xl minus f xm is less than or equal to lip f times distance xl to xm. And that's Cauchy. So that's certainly Cauchy. So both xl and fxm are Cauchy. And yeah, in fact, I guess just said something rather stupid, didn't I? XL is definitely Cauchy, and we're assuming it converges. So completeness or not of X is totally irrelevant. Doesn't matter. It's completely irrelevant. So let's see. We've got this. So that means, oh, I should be using distances here. Because these guys are back in the metric space, XL. So that's fine. That means this is Cauchy. And these are all contained in, this is a sequence contained in Rm. So that's a complete space, so therefore convergent. Convergent. And it's pretty clear that you can then, if you let, say, y be the limit, fxl, say, then you'll get the same limit whatever sequence you pick, as long as you have this same limit point. So, that means we can extend the function f. So I guess that's a general fact that you know anyway, that there exists a Lipschitz extension let's call it f bar from a bar into Rm. So we can work with a bar if we wish. And furthermore, notice that lip of f bar is the same as lip of f. So you can always do that. You can always extend, as long as you're mapping into a complete space, a complete metric space, you can always extend your Lipschitz function to the closure. And you'll get the same Lipschitz constant. All right, so that's good. So we get the same Lipschitz constant, and we've got an extension into a bar. Now let's go back to these sets that we chose. So let's look at the images of those. And let's think about this quantity. Well, let's think about this quantity. Well, notice that f to the minus 1y is contained in the union over the set of y, a set of j, such that y is in the image of Cij intersect A of the image, right? Cij. Yeah, I think I said that right. Oh yeah, we're not too fluent today. Yeah, let's see. Yeah. Right. So I'm supposed to be looking at HK. Sorry, that's the confusion. I'm supposed to be looking at this. So HK is less than or equal to. Okay, let's see. F to the minus 1y is contained in the union of these sets. So if we take the sum of those sets and then take omega k according to the definition of Hausdorff measure, omega k diameter Cij over 2 to the k. Yeah, right. Yes, okay, to the k. That's by definition. We have that. And yeah, so, and that's certainly less than or equal to the sum over j such that y is in Fcij bar intersect A bar omega k diameter Cij over 2 to the k, like so. So we have that. And again, now let's think about this. This is this sum is exactly saying that the sum of the indicator functions over all j, indicator function of this set f Cij bar intersect A bar at y times this stuff, omega k diameter Cij over 2 to the k. Have that. So let's just check that. This is exactly 1 when y is in this set, so you get a term. It's 0 when y is not in the set, so you get 0. You don't sum over that. So it is indeed the same thing.
F bar.
F bar, thanks. This is F bar. Likewise here, this is F bar. That's our extension function. Okay, good. And so we can write that as a in terms of indicator functions. And now let's integrate this. Now there's a slight catch here. Notice that this side is a function of y, and it's a Borel measurable function of y, because this is a Borel set and this is a Lipschitz function. So we proved that the image of a measurable set under a Lipschitz function is measurable. So this is certainly this is actually a Borel set. So no problem about that. But this guy is obvious. In fact, I think I mentioned that these approximating measures behave very badly. They're typically not measurable. So this is not a measurable function. So this is one of the very few times you have to use the upper Lebesgue integral. So I've got to remind you how that works, because I'm about to use that. So recall that if f is a map from, say, space x into 0 infinity, not necessarily measurable. In fact, let's, what have we got? We've got a mapping into, yeah, that's right, not necessarily measurable. Oh, I better, f is our function, so we should call this something else. Let's call it h, a non-negative function. h. And we're just on Rm, so let's leave the discussion just for Rm. So we're in these y's are all in Rm. Okay, so then you can talk about the upper Lebesgue integral. Even though h is not measurable, you can talk about the upper Lebesgue integral. That's simply defined to be the inf over measurable phi with psi bigger than or equal to f of the integral over Rm of psi dln. So that's the definition of the upper integral. It's simply the inf over all measurable functions which are bigger than or equal to f. And if this is finite, what's that? Oh, this is, yeah, sorry, this is h. And notice you can always attain this. There always exists a psi h where this inf is attained. You can very easily do that by using well, there's two cases to consider. If this is plus infinity, and trivially you can find a psi that attains it, just take psi identically equal to infinity. If this is finite, then you just take you take a decreasing sequence of functions which approximate. So always there exists a ch measurable which attains this inf. So no problem. You can always attain this with some particular measurable function. And the other thing that we need is that if you have an increasing sequence, if hi is increasing, take a sequence which is increasing, then this sequence also increases. If this hi increases to some function h, pointwise everywhere, pointwise, this is pointwise convergence. If this sequence increases to some function h, pointwise, then the corresponding sequence of upper integrals converge to integral over Rm of h, which you can easily check using this fact that the thing is attained. So we're going to use this upper integral here. So let's do that. So I'm going to integrate each side of this inequality. On this side, we've got to use the upper integral because that's not necessarily measurable. So we get integral over Rm of hk f to the minus 1y dh ny dlm. We're in Euclidean space, so this is just Lebesgue integral, dlmy, is less than or equal to the integral of this guy, which is just the measure of these things. Sum j equals 1 to infinity. The measure, the integral of the indicator function is just the measure of the set. So that's lm f bar cij bar intersect a bar times this stuff, which is just constant, omega k diameter cij to the k, a diameter cij over 2 to the k, like so. Okay, that's good. And now we're just about finished. So, right, so we have that, and this is 1 over I. And now let's stare at this for a minute. That's Lm of a set. You remember the isodiametric inequality? Lm of a set is less than or equal to, in Rm, Lm of a set is less than or equal to the diameter of omega m times the diameter of the set over 2 to the mth power. That's the isodiametric inequality. So this is less than or equal to sum j equals 1 to infinity omega m, and we already had an omega k, so that's still there, and we get diameter F bar Cij bar intersect A bar over 2 to the mth power, and diameter Cij over 2, so this is omega k. Oh, we've already got that. Diameter Cij over 2 to the k. Okay, that's good. And now this is a Lipschitz function with Lipschitz constant equal to lip f, same Lipschitz constant as the original function. So this is simply less than the diameter of this set times the Lipschitz constant raised to the nth power. So this is less than or equal to lip f to the m times the sum over j of omega m omega k, diameter of this set. Diameter Cij bar intersect A bar over 2 times diameter Cij over 2 to the k. Now notice this is certainly less than or equal to same stuff times, oh, this one's to the mth power. This is certainly less than, clearly less than or equal to the diameter of Cij. We're intersecting with A, so it's certainly less than the diameter of Cij over 2, which is the same as this. So in fact, we get omega k omega m times the diameter of Cij, diameter of Cij over 2 to the m plus k power. And we've got this factor omega m omega k. So let's put these in. Lip f to the m times sum over j times omega m omega k. And let me just artificially put an omega m plus k on the bottom line because I want an omega m plus k on the top line. Because that is exactly what we used here. That's the thing that gets within 1 over I of the size 1 over I approximating Hausdorff measure. So this is less than or equal to lip f to the m times omega k omega m over omega m plus k times h m plus k 1 over I times a plus 1 over I. And now we just let I tend to infinity. Notice this increases up to the Hausdorff measure. So this increases to the Hausdorff measure by definition of the size of 1 over k approximating measures. So that tells us that the upper integral of hm, after we pass to the limit, we just get hm, or rather hk. We get hk of f to the minus 1y is less than or equal to this stuff, lip f to the m times omega k omega m over omega m plus k times just the Hausdorff measure now, m plus k a. So that's the end of the proof except for one slight detail. Can we get rid of that? So let's take a break until just after half past. Well, I went a bit over time today. So let's take a break until half past and we'll continue that discussion. Yep. F is Lipschitz.
How could the fiber F inverse y is not measurable?
Well, but it's, you see, it's not f to the minus 1y I'm worried about. That's measurable.
The function.
It's hk 1 over I of that. That's a weird function of y. You're taking the Hausdorff k-dimensional, you're taking the hk 1 over I measure of that. See that? You're taking, that's a really weird function. Yeah. It's a function of y.
Of the insert image.
So we don't really know much about that. Yeah. Yeah.
That when it's countermeasure, why this phi inverse y is finite?
No, he just
Oh, no, I was just saying that's if it's infinite, of course, then you let n tend to infinity there and you get the correct limit in that case also. No, that was just an example. Yeah, yeah.
You may see one word.
Yeah, 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 yeah.
Does this still hold when you work with this y and the target is also a metric space?
No, there are some restrictions. There are results in Federer, but there are restrictions on the metric space. And the proof is more complicated too. So it's not generally true, but there are some reasonable sufficient conditions on the metric space. I think it's that if all the closed balls are compact or something like that, and maybe some other condition as well, I forget. But the proof is quite a bit more complicated because you can't use the isodiametric inequality. So and this, in any case, works for our present purposes, no problem. Well, it's the only thing.
So the proof is essentially the same, or
No, it's more complicated because you can't use the isodiametric inequality. So it gets more complicated. And you certainly get a different constant as well there, of course, some different constant. So it becomes rather complicated in that case. And I didn't want to get into that because we don't need it anyway. So, yeah.
I think that's quite interesting.
Yeah.
If they want to generalize the whole field to like a general metric space, which includes
Yeah, of course. Right. No, it's certainly of some interest, no question about it, because you often want to look at these slices. So you can imagine there might be situations where you really want to know that. But you can look it up. It's in the section of Federer on Lipschitz functions, not in the measure theory section. It's the section on Lipschitz functions. There's a couple of theorems there. Of course, Federer usually has the best possible results for everything. Right.
leave no room for improvement.
No room for improvement.
But you don't say you just have to reprove this by yourself, and it's
No, he really is amazing. Actually, he doesn't make life easy, but he is hard on himself as well.
You don't remember the
Yeah.
number of it.
but it's in the section on Lipschitz functions. Yeah. No, I only know the number of the co-area formula, 3.2.22. Yes.
So last time you talked about the Whitney.
Yes.
Your statement, you only
Yeah.
have to take the first expansion.
Yes.
So do we have a higher?
Oh, yes, absolutely. Yeah. In fact, all of those theorems are proved in much the same way, using a Whitney partition of unity. And of course, you can guess what the conditions are in that case. You simply take a continuous function, which does extend the given functions, and see what you need. So you read off a necessary condition by assuming you've already got an extension. You see what condition you need. Yeah.
So could you repeat the statement of the covering Whitney for me?
Yeah, it's that you look at the complement of a closed set, which is open, and then a Whitney covering is a covering with the property that it's a partition of unity of that open set, and it has the additional properties that that any given so you've got these functions, this partition of unity, so functions with compact support that add up to 1. So you look at the supports of these functions. Now, what you have to have, if it's going to be a proper Whitney partition, is that each support of one of those functions intersects at most a fixed number of the others, of the other supports, where the number of those is bounded. So it goes like this. It's see, and I'm drawing the supports here now.
Okay.
Now notice this one is intersected by at least 2. In fact, it could be a lot more. There could be several here. So this set in here is got 1, 2, 3, 4, 5, 6 that intersect it. And if it's going to be a Whitney partition, there has to be a fixed number n, so that that number of possible other supports that intersect a given support is bounded by n. And one other condition also, that the diameter of these has to be proportional to the distance to the set. Distance to the set. Not exactly proportional, but to within specified constants, which again are fixed.
So could
Yeah.
could the fitting covering kind of covering of the entirely covering that kind of thing?
No, it's actually, it isn't that hard to prove once you realize what you need to do, but it's not easy either. It's a tricky argument. Yeah. There
are lots of covering for
Yeah.
Polish school.
Right,
Polish.
right, that's
so
right.
This cannot be the covering of that for the
Yeah.
Polish school.
No, I think this
forget
is,
the name.
no, I don't think so. I think this was Whitney's original idea. I'm pretty sure. Because it's always referred to as a Whitney partition of unity. Yeah, yeah. Yeah. Actually, this extension was only in Euclidean space, so we're working in Euclidean space here. I don't think such a theorem would be true in general metric space. You'd have to make very serious assumptions about that.
Professor, can I ask a question?
Yes.
Why there is this phi x?
You assume that all these psi's are measurable, and you take the inf over all of those. And in the case when this left-hand side is finite, you want to prove that you can attain that inf. Okay? So you take a sequence of psi's, which converges to the inf, each of which is bigger than or equal to h. Right? And then you take the minimum of the first j of those. That's an increasing, you take the minimum of the sequence from j to infinity. Take the inf of the sequence from j to infinity. That gives you a new sequence which is decreasing and which is still bigger than or equal to h. And then you just use the dominated convergence theorem then. Yeah.
How does, where do we use the function of f bar?
Because we needed that to be a measurable function on the right.
Yes, but so in the previous proposition,
Yes.
we don't need to do the f bar extension. But why here we need to do the f bar extension? Previously,
You see, we need the f bar because the c bar intersect a bar is not contained in the domain. F's only defined on a. You see.
Yes.
So you need an extension that's defined on a bar.
So when we choose the Cij, how we choose the Cij to be close?
You could do that, but you'd still have a problem. Then you could choose the Cij to be closed. Right? Yeah, maybe that's probably maybe you could avoid that. Actually, I thought there was a problem with that, but maybe you're right. Let's see. Is there any reason you couldn't do that? I thought that,
we are not using the
maybe. No, I thought there was a reason why we couldn't do that. So these can be closed, and this is measurable. So these are these are measurable. I thought there was some reason that doesn't work. Maybe I'm wrong. I've got to think about it. I'm not sure, actually. You may have a point, but I thought there was some point there to that.
In any case, this is a good property.
Yeah, it's a nice property to know. Right, that's right. Yeah. Okay. Okay, so let's continue. So I just wanted to talk about this last point here, that we would like to get rid of that. And in order to get rid of that, we've got to know that this is a measurable function of y. This is the k-dimensional Hausdorff measure of the pre-image under a Lipschitz map. Now, it turns out, yes, indeed, that is a measurable function of y. In fact, that's one of this week's assignment problems. Note. F to the minus 1. Of course, not from scratch. The question is set out in 3 steps to help you along with appropriate hints at each stage. F to the minus 1y is an HK measurable function. Function of y, and that's problem 2.8. And keep in mind that to solve that correctly, there's one subtlety. First 2 parts of problem 2.8 are fairly easy, but then you've got there's a slight subtlety about sets of measure 0. Sets of HM plus K measure 0. But if A's got M plus K measure 0, that means that this is a null set. Since we've already proved this so far, that means that this is a null set, HM almost everywhere. So you can make use of that using the definition of upper integral. So yeah, so that's so we're modulo that we are done then. This is correct. Okay, so now let's, so for the remainder of today, I want to talk about the area formula, extremely important formula. So the area formula and here we're taking a Lipschitz function from Rn to Rm, and we'll later talk about mapping a submanifold, a slightly more general situation where a Lipschitz function is given on a submanifold instead of on the Euclidean space. But this is the main ingredient of that. And here the crucial point is that this has to be bigger than or equal to that. So we're mapping from a lower dimensional space into a higher dimensional space. And this is Lipschitz. And keep in mind that Rademacher guarantees, as we proved last time, Rademacher's theorem guarantees that F is differentiable almost everywhere. So Rademacher, we're going to make use of this in the proof. Rademacher guarantees that F is differentiable Ln almost everywhere in Rn. And that means that Fy minus Fx minus, let's call it dfx y minus x. So dfx is the induced linear map. That's dfx v is equal to the sum j equals 1 up to n vj partial, jth partial of f. Or another way to say that, it's the same as the directional derivative in the direction v of f, and this is at the point x. Or yet another way to say this is that df is the linear map, dfx is the linear map from Rn to Rm, same dimensions as we started with. F is mapping Rn to Rm, so this is the same, except that this is a linear map and it's got matrix DIFJ X. That's an m by n matrix. Or is it n by m, I guess. It depends on what your convention is. Anyway, the i's have got n components and the j's, so there are, if j is the column index, then there are m columns and n rows. So that's, we have that property. So we're going to make use of that, and we're going to also define the so-called Jacobian, or the area magnification factor, sometimes referred to. And JF at x is defined to be the square root of the determinant of DIF at x. Now notice that's a vector in Rm. And you take DIFX dotted, that's the dot product in Rm, with DJFX. So DIFX dotted with DJFX. That's an n by n matrix. And so it makes sense to talk about the determinant of that. Notice another way of writing that in terms of this induced linear map is that it's the square root of determinant of dfx at dfx adjoint. In terms of matrices, that's the adjoint matrix. That's given by the adjoint matrix. That's the matrix DJFI, composite with dfx. So that's another way to write that. But this is usually the simplest formulation. Just take the matrices and take the vectors that you get by, so it's the ith partial derivative of the vector function dotted with the jth partial derivative of the vector function. That's a nice way to compute it. So this is, so this makes sense, and that's what JF is. Then what's true is the following. That let's also take a set, let's say it this way. An integral over A of JFX DHN x is equal to the integral over Rm of H0 of f to the minus 1y. So it's the counting measure again. Counting measure. Remember, this is the number of points if this happens to be a finite pre-image. Otherwise, it's plus infinity. Or it's 0 if it's, of course, it's 0 if it's empty. In other words, if y is not in the image, this is 0. And this is DHN. DHN. Yes. And again, this looks sort of weird, but remember what you're really doing here is integrating over FA, because in any case this is 0 when y is not in the image space. So you can write it either way. So that's the area formula. And let's just check that it works out the way we think it should work out with a few examples. Before I give the proof, let's compute a few examples. Well, first thing to note is that if f is 1 to 1, that is, each pre-image is just 1 point. Each pre-image of an image point is just 1 point. So there's only 1 point that maps to every image point. There's just 1 point in the pre-image. It's a one-to-one function. If f is 1 to 1, then this just is 1 everywhere in the image. So this just says that then the right-hand side here, the right-hand side is simply the n-dimensional Hausdorff measure of FA. So that's the way to think of this. It actually gives you a formula for the n-dimensional Hausdorff measure of the image, at least if f is 1 to 1. And if f is not 1 to 1, it's a refinement of that. It's the integral over the image of the number of points in the pre-image. So it's a very precise formula. So let's give a couple of examples that'll make clear that we're on the right track here. First example is, let's take a one-dimensional example when you just look at curves. So that would be the case n equals 1 and m bigger than or equal to 1. And in this case, let's take A to be the closed interval A to B contained in the real line. And let's, instead of calling it F, let's call it gamma. So gamma is a map from AB into Rm. So in this case, this is our set A. Okay, let's compute the Jacobian then. And this should at least be Lipschitz. Let's compute the Jacobian. So the Jacobian, we take di dotted with dj. In this case, there's only one variable. Let's call the variable t, variable in the interval ab. So we in this case, j gamma of t is equal to the square root of the determinant. Well, in this case, it's not really a determinant. It's just the real number. There's only one index, so it's the derivative of gamma dotted with itself. So that's the length of gamma prime t squared. Dot product of gamma prime with itself. That's the length of gamma prime t squared, which is, of course, just the absolute value of the vector gamma prime t. Notice this is the length of the velocity vector of the curve. Length of the velocity vector of gamma. And so that says, so let's see what it says now. That means that this becomes integral from A to B of length of gamma prime t dt equals the integral over Rm of h0 times gamma to the minus 1, the pre-image, of y dh1, in this case n is 1, so it's dh1, one-dimensional Hausdorff measure. Now if gamma happens to be 1 to 1, so so we've got this picture, here's AB on the real line, and gamma's mapping is a curve mapping into Rm. So Rm's here, and you've got a curve. And gamma A may be here, and gamma B may be here, for example, like so. And if gamma happens to be 1 to 1, so the curve doesn't intersect itself, so then this is 1, as I mentioned before, except when you're not in an, it's either 0 or 1, depending on whether y is in the image set or not. So this just is equal to the one-dimensional Hausdorff measure of the curve gamma, of gamma of AB, one-dimensional Hausdorff measure of the image curve, if gamma is 1 to 1. That's good, because that's exactly what, remember, you probably saw the proof of this in some calculus course somewhere. So indeed, the one-dimensional Hausdorff measure, which is the length of the curve, is indeed given by this classical formula. So that seems to work. That seems to be in agreement with the classical calculus theory. But what about the case when the curve, I mean, keep in mind that the curve may decide to do something rather weird. It may decide to turn around and come back and stick to itself for a while. Now, in that case, the one-dimensional Hausdorff measure will be too small. It won't, the thing on the, so that's when this comes into play. Notice that the multiplicity is 2. If y is in this set, then the multiplicity is 2. h0 gamma to the minus 1 y is equal to 2 in this set here. So this would be integrating with respect to h1 over this bit of the image set times 2 plus the integral over this set of these bits of the image set times 1. Well, that's correct, isn't it? That's exactly what the length should be. So it does give you the length, exactly. Even in these complicated cases when the curve may decide to stick to itself on, might even stick to itself on a fractional dimensional set. It could do all sorts of weird stuff. But still the formula is correct. You get the correct, this is the correct formula for that. So the formula works extremely well there. So let's look at a more classical situation when you have a submanifold of Euclidean space, which we'll talk about next time in some detail. But for the moment, I guess everyone knows roughly what I mean by a submanifold. Smooth n-dimensional surface sitting in some Euclidean space, Rp, say. And this is, so here we're still in, let's call it n plus k, say. And this is n-dimensional, so think of this as an n-dimensional surface. And suppose that we have a so-called local coordinate representation. So down here in Rn, this is Rn down here, we've got some open set V, and we've got a mapping which we call Psi. This is a local coordinate mapping. We'll discuss all this in some detail next time. Local coordinate map, C1, at least, let's say, at least C1 anyway. If you want to C1 in general, you might assume that it's CQ for some Q. And suppose it's at least C1, and the image is then some set up here. So this is the image set, psi phi. And of course, a local coordinate representation by definition is 1-to-1 and C1. So we'll say more about that next time. So what does the area formula say in this case? Well, the area formula is given by this, so let's compute. The Jacobian, in this case, J of C at x is just the square root of determinant of di psi dotted at x, dotted with dj psi at x. And that's what the differential geometers would call root G, where the Gij is the matrix. This is a Dij, the differential geometers would call this the metric in the local coordinates down in this space V. So x is down here. So metric in local coordinates. And Gij is exactly this matrix. That is the classical formula from Riemannian geometry for the metric in local coordinates. And then the square root of the determinant is usually denoted square root of G in differential geometry discussions. So this, in this case, the formula says, well, in this case, again, this is just 1 when you're in the image set and it's 0 elsewhere. So C is 1-to-1. So in this case, we get integral over A. A is a subset down here in V. So you take any set down here in the coordinate, in the local coordinate space, and call that A. Then the area formula says the integral over A square root of G is equal to the n-dimensional Hausdorff measure of CA. Or if you want to say it another way, if you take a set, say take a set B up here in the image space, then you can look at the pre-image down here. So that's equivalently, so integral square root of G taken you take the pre-image of a set B from upstairs, look at it downstairs, take the pre-image. This, by the way, is integral with respect to n-dimensional Lebesgue measure. Equals the integral over B, is just the n-dimensional Hausdorff measure of B. So indeed, this is exactly what, so what's the point here? The point is that indeed, n-dimensional Hausdorff measure on a smooth submanifold, on a C1 submanifold of Euclidean space, is indeed exactly the classical thing that differential geometers would call the volume measure. So indeed, Hausdorff measure is the volume measure. So indeed, as I claimed earlier, Hausdorff measure is the natural generalization of Lebesgue measure to a much more general situation. Okay, so that's the story there as far as some examples are concerned. Let me give you one more example. A third example, when you're looking at a graph, when you take a graph, so you let U be, so you let V be a domain in Rn, and you let U be a mapping from Rn to R, and let it be C1, say, and then look at the area formula for the graph map. We want to look at the graph of U. The graph map is the map that takes a point X downstairs in V to the point on the graph. That is the point on the graph of this function U. So it takes X in V to the image point X Ux in the graph of U. It's the so-called graph map. And notice this is all contained in Rn plus 1. So in this case, m equals n plus 1. And let's see what the area formula says in this case. So we've got to compute the Jacobian again. Okay, this looks a bit more challenging. Well, in this case, this is our map F, this thing here. So I've got to take the ith partial derivative of this thing, di of x ux. Okay, but that's easy. The ith partial derivative of x is just the ith basis vector, ei, and the ith partial of u is the ith partial of u. So that's that. And now we take, so that means that Jacobian in this case, let's call this capital U, the graph map is capital U. So that means the Jacobian of the graph map at x is exactly equal to square root of the determinant of this ei diu x dotted with ej djux. And that's ei dotted with ej is the Kronecker delta ij. So this is the square root of the determinant of the n by n matrix Kronecker delta ij, which is the identity matrix, plus diu times dju. Okay, so who are the good linear algebra people here? You know how to compute something like that? The point about this is that it's identity plus a rank 1 matrix, and you can easily compute that determinant by computing all the eigenvalues. And then the determinant is the product of the eigenvalues. So when you work that out, you'll find you simply get square root of 1 plus dux squared, length of dux squared. So in this case, and of course this is a one-to-one map, obviously, because it's one-to-one even with respect to the first n coordinates here. So it's a one-to-one map. So that means in this case we just get that hn of the graph of U, the n-dimensional Hausdorff measure of the graph of U, is equal to the integral over V of square root 1 plus du squared, integrated with respect to n-dimensional Hausdorff measure. And I think you've seen that formula before in calculus books, right? That's the standard formula for the volume of a graph. So there's 3 examples, and everything seems to work out very nicely with those 3 examples. All right, so let's see if we can prove the, at least let me start the proof of the area formula. As I said, that we're going to be using this Rademacher theorem. That's sort of the main tool in the proof. So remember, Rademacher's theorem says limit y minus x to minus 1, y tends to x, is equal to 0, for Ln almost every x in A. Yeah, Ln almost every x in A. So we have that to work with. So let's use that fact. So the proof okay, so I'm going to break the proof into several cases. Case 1 is the main case. That's the case when f is differentiable for every x in A. Notice it's really only differentiable for almost every x, but just let's first look at the case when it's differentiable for every point x in A. That's just one case. And furthermore, that a dfx, that's this linear map induced, that's this thing up here, dfx has rank n for every x in A. So let's look at that case. So this is actually the main case. The rest of the proof is fairly easy once you've got this case. And so let's make an observation about, first of all, about these sort of functions here. This, remember, in terms of the induced linear map, this is dfx adjoint composed with dfx. So let's first of all make a couple of observations about maps like that. Suppose lambda is a linear map from Rn to Rm. So keep in mind we're going to apply this to the lambda equals dfx, right? Because dfx is a linear map from Rn to Rm. So suppose lambda is a linear map from R and it has rank n. Now keep in mind rank n is the maximum it could be. You can't have a map with rank bigger than n when the domain is only, that's nonsense. So this is the maximum rank that you could have. And look at lambda star composite with lambda. That's a map from Rn back to Rn. The adjoint composite with the map. And notice that that map is symmetric. Means it's represented by a symmetric matrix, obviously. And in fact, you can write down what the matrix is. If you give the matrix of lambda, you can work out what the matrix for that is. So it's symmetric, and it's also positive definite. So suppose rank n, symmetric, positive definite. And let's check that. Positive definite. Let's check that. So lambda star composite lambda. To check something's positive definite, you've got to apply it to V and then take the dot product with V. Well, by definition of adjoint, that's the same as the length of lambda. It's the same as lambda of V dotted with itself. That's the definition of adjoint. Adjoint definition says that this is actually equal to lambda V dotted with lambda V. So this is the length of lambda V squared. And that must be non-zero for every V, otherwise it wouldn't have rank n. The null space must be 0, right, in this case, otherwise it can't have rank n. So this is positive for every V not equal to 0. So so it's symmetric and positive definite. But then we can use the spectral theorem, remember. That means that there's a symmetric, that there's an orthogonal transformation Q, so there exists an orthogonal Q from Rn to Rn with Q star times this symmetric positive definite thing, Q, equals a diagonal matrix. And let's call it lambda. And in fact, the diagonal matrix has got positive entries down there. The eigenvalues are all strictly positive here because it's a positive definite matrix. So this is lambda 1 down to lambda, oh, I better use a different symbol, mu1 down to mu n with zeros everywhere else, so it's diagonal, and mu j bigger than 0 for every j. Now stare at that for a minute. You can rewrite this as square root of lambda times the square root of lambda, just the square root of lambda squared, where square root of lambda means the matrix, the diagonal matrix with square roots down here, right? So it's square root of lambda times square root of lambda. And we can put these q's over onto the right. If I multiply from the left by q, I can use q star equals identity. If I multiply by q star from the right, I can use q star equals the identity. So this tells us that the original thing, lambda star composite lambda, is equal to q times square root of lambda times square root of lambda times q star. And then I can squeeze in another q star q in here because that's the identity anyway. And you see, then we can remember composite of linear maps is associative, so you can put the brackets wherever you like. And so we can bracket it like that. And notice this is just the square, tor squared, where tor is this guy. Tor is q square root of lambda times q star, which is an n by n symmetric matrix, rank n. Of course, it's rank n because this has got a diagonal with positive entries down the diagonal. So everything's rank n here, symmetric rank n. So you can always use lambda composite lambda star. It can be written as tor squared. Very convenient fact, where tor is a symmetric. Notice it's symmetric because if you take the adjoint, you remember adjoint reverses the order and puts adjoint on everything. The adjoint doesn't change this guy because it's diagonal. So you can always do that. So let's agree on that. And yeah, and I'm not sure what happened where. Oh, here it is here. Right. So we can apply that to this. Now, so let's think about this. So let's think about these things. These are maps. This lambda is a map from Rn to Rm, a linear map from Rn to Rm. And dfx is one of those. It's one of those maps. And so let's just take a countable dense subset of the linear maps from Rn to Rm. So let lambda 1, lambda 2, etc. be countable dense in the space of linear maps from Rn to Rm. Let's do that. So, of course, that's clearly okay, right? I mean, each of these is represented by an n by m matrix. So this is really just saying you can take a countable dense set of points in the appropriate open set in the Euclidean space Rn times n, that high-dimensional Euclidean space. You can just look at the matrices. So certainly you can do that. Take a linear maps. And then we can stare at this thing a bit. Notice that this limit implies that for every epsilon bigger than 0, there exists a delta x, depending on x, positive, with fy minus fx minus dfx y minus x less than or equal to epsilon times length of y minus x. However, we can, this is not such a convenient, that's true, and that's true for every y in the ball of radius delta x. centered at x, except of course for the center point where well, actually, it's even true for the center point as long as you write a less than or equal to there. So it's true even at x because both sides are 0 when y is equal to x. So it's even true there. So it's true in the whole ball. But this is not so convenient for us at the moment. Let's make an additional observation here. Notice that this is never 0, as I said. When you take a rank n map, you always see this. You can always do this thing. It's always positive, never 0. So that means that the inf over v in Rn with the length of v equals 1 of dfxv, that's positive. So, and I can improve it. I could have taken any constant I like. So you see, well, another way to say this is for v length 1, but notice this implies that there exists a constant, c, depending on x, bigger than 0 with dfx v bigger than or equal to that constant times the length of v. And now v no longer has to have length 1 now. This is for every v in Rn. So you always get this fixed constant times that. So I can actually make, for that reason, I can, as long as I pick a smaller epsilon, I can make this side actually less than dfx y minus x times epsilon. And I can even put an epsilon over 2 there if I want. Do whatever you like. You can make it as small as you like, so no problem. So that's a nicer way to write this. So we do that. Notice we strongly use the fact that the rank was n there. Otherwise, we wouldn't have been able to use this inequality. Okay, that's good. And now, now what does that say? Well, now we've got dfx here and here. So, and we've also got a countable dense set of lambdas that can approximate as close as you like to these dfx and this dfx, both places. So I can pick a lambda j that's as close as you please to a dfx. The lambda j's are dense in the space. So as long as I'm willing to give up a little bit, for instance, I'm willing to make that epsilon over 2 into an epsilon, then I can replace dfx by lambda j in both places for suitable j. So hence, there exists lambda j, there exists a j. This is a linear map from Rn to Rm, one of the lambdas in that countable dense set with fy minus fx minus lambda j of y minus x less than or equal to epsilon. I had to give something up. You see, I replaced epsilon over 2 by epsilon. But lambda j appears everywhere now instead of x. And that will be true for every y. And let's, that'll certainly be true for every y in a sufficiently small ball. It's this guy here, but I can make it for every y in, say, the ball of radius 1 over I, centered at x, provided I is large enough, for large enough I. So we can arrange that. So now this is starting to look a bit more sort of controllable because we've only got countably many of these things. Radius is countable, the lambda j's are a countable set. So somehow that looks more manageable. And then let's just use a triangle inequality here and put the lambda j onto the right in both directions. So that means that fy minus fx is bigger than or equal to 1 minus epsilon. Let's agree that epsilon's between 0 and 1. No problem. So I get 1 minus epsilon times the length of lambda j y minus x and less than or equal to 1 plus epsilon times the length of lambda j y minus x. And that's for every y in B1 over I x. So that's good. That's looking better. And one further simplification here is that, remember, one of the things we know about these maps is that you can do this Tor thing and then notice that the length of lambda v squared, that's this thing, is exactly the same as the length of Tor v squared. And while we're at it, let's also notice that if you take the determinant of this, this is the same as that, same as this. So determinant of Tor squared, remember the matrix, taking determinants is, if you take the determinant of a square, it's the same as the square of the determinant. So determinant Tor squared is the same as the determinant of that guy, lambda star composite lambda. And then we can take square roots. So we get the absolute value of the determinant is the square root. The determinant lambda star lambda. Now for us that's good because this... Yes?
Does epsilon depend on x?
Yes, it does. No, epsilon is given, but delta x depends on x and f and everything else. But epsilon is just a fixed... For the moment, epsilon is just a given number. Yeah. It doesn't depend on anything. It's just a fixed number. And the claim is that you can pick a j. What we've shown is that you can pick a j so that this is true for every y in B1 over Ix. Okay. And for large enough I, and that depends on x. Very important, of course. You can't just take a fixed I to work for all x. It depends on x. And remember, we're taking x in A, and we're assuming that f is differentiable at every point of A at the moment. This is case 1. It's got rank n, and so this is fine. So let's record this. So that means for lambda I, we get a Tor I. So we can also replace this by Tor. So I can replace this, but that is 1 minus epsilon times Tor j rather, of y minus x is less than or equal to fy minus fx less than or equal to 1 plus epsilon times Tor j y minus x for every y in B1 over I. And again, let me emphasize, it's for large enough I, but that depends, which I depends on x. You must keep that in mind. Okay. Now, let me also record, so this is 1, and let me also record the fact that det Tor I is the same as det lambda, so det Tor I absolute is det square root of det lambda j star composite lambda j. By the way, you have to resist the temptation to say that this is the same as det lambda squared, because lambda is not a square matrix. It makes no sense to talk about determinant of lambda. The best you can do is talk about this determinant of that, lambda j. So we have that. And notice, by the way, that these lambda j's are approximating, we chose the lambda j's to approximate this, right? So actually, I can also arrange so that this is less than or equal to 1 plus epsilon times the Jacobian jfx, because the Jacobian is the square root of this guy, determinant of this guy, this square matrix, determinant of this guy. And lambda j approximates that. So I can arrange that, and I can arrange that it's bigger than or equal to 1 minus epsilon times jf x. So that's nice. We can sort of approximate everything, including the Jacobian. We can approximate the function very precisely in terms of these Tor j's, these symmetric guys, and we can also approximate the Jacobian in terms of the det Tor j. Tor j, like so. So we have these, and I'm going to find that let's say, let Aij, let Ai, yeah, so there's two indices here. There's an I and there's a J, right? So let Aij be the set of X in A such that this is true. Let's call this star. Star holds. Now notice, by definition, star does hold for large enough I and a suitable choice of J. You can do that for every X. So that means that A is indeed the union of all the Aij's. Very important. We get the whole of A. Notice it's not a disjoint union, but we do get a breakup of the whole set in this way, countable union. Okay, so that's about as much as we have time for today. So we'll pick it up next time from this. I'll start at this point. This is really the main step of the proof, actually. Once we've got this, the rest of the proof is surprisingly straightforward, actually amazingly so. It looks like we've made no progress, but actually we're almost finished. So we'll continue from there next time. Oh yes, we've got to pick up the assignment.
I mean the assignment for homework 3.
Homework 3, yeah, it's on the web page. Week 3, oh yeah, that's the other thing. Did everyone get an email from me?
You already sent an email.
Did anyone not get an email from me? Okay. No, okay, good. So week 3 is problems 2.6 and 2.8. But make sure you've got the latest version. Make sure you've got the updated version, which was updated earlier today. Because I made a correction to problem 2.6, and I also added a hint there. So, right.